Welcome to Opulenta.ai. I am Opulenta. Let's discuss how to rewrite Floyd's algorithm to use recursion. Floyd's algorithm is a well-known shortest path algorithm used to find the shortest path between two nodes in a graph. In this document, we will explore a modified version of Floyd's algorithm that utilizes recursion. The recursive approach allows for a more intuitive and elegant implementation of the algorithm. When we say that the recursive approach allows for a more intuitive and elegant implementation of the algorithm, we mean that using recursion can make the code more straightforward and easier to understand. Intuitive. Recursion often closely resembles the natural structure of the problem being solved. In the case of Floyd's algorithm, the problem can be naturally broken down into subproblems of finding the shortest path between nodes. The recursive approach aligns with this natural structure, making it easier to grasp the logic of the algorithm. Elegant. Recursion can lead to more concise and elegant code compared to iterative solutions. By dividing the problem into smaller, self-contained subproblems, the code becomes more focused on the core logic and reduces the need for complex loops and state management. This can result in cleaner and more readable code. In the case of Floyd's algorithm, the recursive approach allows us to express the problem as a set of recursive calls, where each call solves a subproblem by recursively invoking itself. The recursive calls capture the essence of the algorithm in a straightforward and elegant manner. However, it's important to note that while recursion can offer elegance and clarity, it may not always be the most efficient solution in terms of performance and memory usage. Care should be taken to handle large input sizes or cases where deep recursion could lead to stack overflow errors. In such cases, an iterative or optimized approach may be more suitable. Let's illustrate the concept using an example and a matrix representation. Consider the following graph represented by a distance matrix. In this matrix, the value INF represents an infinite distance or no direct path between nodes. The value at graph I(j) represents the distance from node I to node j. Now, let's apply Floyd's algorithm to find the shortest paths between nodes in this graph. Initialization. Start with the given distance matrix. Set the diagonal elements to 0 since the distance from a node to itself is always 0. Iterative updates. For each node k from 0 to n1, where n is the number of nodes, consider it as an intermediate node. For each pair of nodes I and j, check if the path through node k improves the shortest path between I and j. If graph I(j) greater than graph I(k) plus graph k(j), update graph I(j) with the new shorter distance. After the iterations, we have the final updated matrix, where each element graph I(j) represents the shortest distance between node I and node j. In this example, the algorithm didn't find any shorter paths during the iterations, so the matrix remains the same as the initial matrix. The iterative updates allow the algorithm to consider all possible intermediate nodes and evaluate if they improve the shortest paths between pairs of nodes. This process continues until all nodes have been considered as intermediates. By iteratively updating the distance matrix, Floyd's algorithm efficiently computes the shortest paths between nodes in a graph. I hope this example helps clarify how the algorithm iteratively updates the matrix to find the shortest paths. Recursive Floyd-Warshall algorithm. To begin with, let's understand the essence of Floyd's algorithm. The algorithm works by iteratively updating a matrix that represents the distances between nodes in the graph. Each iteration considers a specific node as an intermediate node and checks if it improves the shortest path between any pair of nodes. If a shorter path is found, the matrix is updated accordingly. Now, let's adapt Floyd's algorithm to use recursion. The recursive version will consist of a main function, Floyd_recursive, which takes the distance matrix as an argument. Let's look at the code. Def Floyd_recursive, distance. A recursive implementation of Floyd's algorithm. Def helper, start_node, end_node, intermediate. Hashtag base case. If start_node and end_node are the same, distance is 0. If start_node equals end_node. Return 0. Hashtag recursive case. Calculate the minimum distance. Return minute. Helper, start_node, end_node, intermediate. Helper, start_node, intermediate, plus helper, intermediate, end_node, intermediate. Hashtag perform recursive calls for each combination of nodes. For intermediate in range, max_length. For start_node in range, max_length. For end_node in range, max_length. Distance start_node, end_node, equals helper, start_node, end_node, intermediate. Print, distance. Hashtag test the recursive version of Floyd's algorithm. Floyd_recursive, graph. In the recursive version, we introduce a helper function, helper, which calculates the minimum distance between two nodes given an intermediate node. The base case of the recursion occurs when the start_node and end_node are the same, resulting in a distance of 0. The recursive case utilizes the helper function to calculate the minimum distance. It recursively calls itself, splitting the path into two parts, from the start_node to the intermediate node and from the intermediate node to the end_node. The minimum distance is then computed by taking the minimum of the current distance and the sum of distances from start_node to intermediate and intermediate to end_node. Let's break down the explanation of the recursive version step by step. Introduction of the helper function. In the recursive version, a helper function named helper is introduced. This function calculates the minimum distance between two nodes given an intermediate node. The purpose of this helper function is to encapsulate the recursive logic and provide a convenient way to calculate the minimum distance. Base case of the recursion. The base case occurs when the start_node and end_node are the same. In this case, the distance between them is considered 0 because they are the same node. This base case serves as the stopping condition for the recursion. When the base case is reached, the recursion stops, and the result is returned. Recursive case. In the recursive version, the helper function is recursively called to calculate the minimum distance between two nodes. The recursive case involves splitting the path into two parts, from the start_node to the intermediate node and from the intermediate node to the end_node. The helper function is called recursively, passing in the updated start_node, intermediate node, and end_node. At each recursive call, the minimum distance is computed by taking the minimum of the current distance and the sum of distances from start_node to intermediate and intermediate to end_node. The recursion continues until the base case is reached, and then the computed minimum distance is returned back through the recursive calls. In summary, the recursive version of the algorithm utilizes a helper function to calculate the minimum distance between two nodes. It recursively calls itself, splitting the path into two parts, and computes the minimum distance by taking the minimum of the current distance and the sum of distances from start_node to intermediate and intermediate to end_node. The recursion stops when the start_node and end_node are the same, resulting in a distance of 0. By using recursion, the algorithm elegantly handles the computation of the minimum distance and simplifies the implementation logic. It allows for a more intuitive representation of the problem and can be easier to understand and reason about. The main Floyd_recursive function iterates over each combination of start_node, end_node, and intermediate, calling the helper function to update the distance matrix accordingly. In this adaptation of Floyd's algorithm, we have successfully transformed the iterative solution into a recursive one. The recursive approach provides a clearer and more concise implementation of the algorithm. By breaking down the problem into smaller subproblems, we can calculate the minimum distance between nodes effectively. To ensure the quality and reliability of the code, it is essential to adhere to the PEP standards, utilize source control, and write comprehensive unit tests. Additionally, performance tests should be conducted to compare the efficiency of the recursive version against the iterative version mentioned in the provided PDF. Analyzing any performance differences between the two implementations can be done by formulating hypotheses and investigating factors such as function call overhead and memory usage. The report should discuss the development process, test coverage, and provide insights into the observed performance variations. Here's an explanation of the mentioned points. Adhering to PEP standards. PEP stands for Python Enhancement Proposal, which provides guidelines and best practices for writing Python code. Adhering to PEP standards ensures that the code is written in a consistent and readable manner, making it easier for others to understand and maintain the code. Following PEP standards includes aspects like code formatting, naming conventions, comments, and documentation. It promotes code quality and readability. Utilizing source control. Source control, such as Git, allows for versioning and managing changes in the code base. By using source control, you can track and manage different versions of the code, collaborate with others, and easily revert changes if needed. It is crucial for maintaining the integrity of the code base, coordinating team collaboration, and ensuring that the code remains stable and reliable. Writing comprehensive unit tests. Unit tests are written to verify that individual units of code, such as functions or methods, work as expected. Comprehensive unit tests help in detecting bugs, ensuring the correctness of the code, and providing confidence during code modifications. By writing tests for different scenarios and edge cases, you can increase the reliability and robustness of the code. In the context of the algorithm implementation, unit tests should cover various scenarios to validate the correctness of the shortest path calculations. Conducting performance tests. Performance tests are designed to evaluate the efficiency and speed of the code. In this case, performance tests should compare the efficiency of the recursive version of the algorithm with the iterative version mentioned in the provided PDF. By measuring factors such as execution time, memory usage, and CPU utilization, performance tests provide insights into the performance differences between the two implementations. Analyzing performance differences and formulating hypotheses. The performance differences between the recursive and iterative versions can be due to various factors, such as function call overhead and memory usage. To understand these differences, hypotheses can be formulated based on observations and knowledge of the algorithm and programming concepts. The hypotheses can then be tested and validated through performance tests and analysis. For example, one hypothesis could be that the recursive version incurs higher function call overhead due to the recursive nature, leading to slower performance compared to the iterative version. Including insights in the report. The report should document the development process, including the steps taken to adhere to PEP standards, utilize source control, and write unit tests. It should provide details about the test coverage, explaining which parts of the code were tested and how thoroughly they were tested. The report should also discuss the observed performance variations between the recursive and iterative versions, presenting insights into the factors that contribute to these differences. By analyzing the performance differences and providing insights, the report adds valuable information about the strengths and limitations of each implementation. In summary, ensuring code quality and reliability involves following PEP standards, using source control, writing comprehensive unit tests, and conducting performance tests. Analyzing the performance differences between the recursive and iterative versions helps identify factors that contribute to variations, and these findings can be discussed in the report to provide insights into the observed performance differences. Please feel free to have a look at our website and go to the blog section to read more. www.opulenta.ai. Subscribe to our YouTube channel to keep up to date. If you would like any specific help, contact us on result@opulenta.ai. Thank you for watching. Bye.